quite by accident, we happened upon Professor Ian Stewart, who kind of has probably broken the golden rule, and he's made math fun. And one of the other things that I found, which was really funny, he's, I think, one of the only known wizards that I know. He's actually been crowned a wizard of the unseen university. So welcome, Professor Ian.
Speaking about Pythagoras, I have to ask you this question. I'm sure millions like me want to ask you this question. Why did I study the Pythagoras theorem? I've never measured a hypotenuse in my life, ever.
You studied it so that you were one of the people who might later on become an engineer who would build something like satellite navigation system. Young children are absolutely fascinated by numbers, by shapes, by colours, by arranging things, making patterns. I think that gets lost. It gets lost under the pressure of getting the answers right, passing the exams, getting a good grade on the latest assessment or whatever. I would like to see this playful side of mathematics develop better. Mathematics is fun. You don't have to make it fun. You just have to stop destroying the fun.
So there was this show I saw where this professor was teaching, and he was talking about pi. And so naturally, one of the kids raised their hands and said that, this sounds great, but where, what does it do for me? I have no relation to this number. And so he said something very interesting. And so he said that obviously pi is a non-recurring number. So he said that embedded within this number sequence is your life's history. It's your bank PIN number. It's your social security number. It's your girlfriend's birth date. It's everything that you ever know is hidden within this string. I very distinctly remember the situation in a movie where there was this kind of a buffoon and there were these smart guys, and they were trying to demonstrate to each other how that buffoon is a buffoon. So they say that, we offer him 25p and we offer him 1 rupee, and guess what he takes? He always takes the 25p. And they kept on doing this. You said, see, I'll prove it to you again, I'll prove it to you again. And then towards the end of the movie, the story flips towards the side of the buffoon. And they said that, did you know that 25p was better or the 1 rupee? He said that if I had taken the 1 rupee, would they have offered it to me 20, 30 times? So I made more money. So he obviously had the smarter thing going there. So,
that is absolutely brilliant.
So, welcome to another episode of Three Techies Banter. As you're all aware, we started this podcast to make technology fun and interesting and conversational. And in the process, we realized there are lots of other things that are also equally, terrifying, if that word could be used. And one of them is... I think for a lot of people is math. So we said, what should we do to make math interesting? And quite by accident, we happened upon Professor Ian Stewart, who kind of has probably broken the golden rule, and he's made math fun. So, and that is not to say he is a non-serious person. He's written over 120 books. He's written about 200 peer-reviewed papers. He's a fellow of the Royal Society. One of the most interesting things is that he used to write a column called Mathematical Recreations for the Scientific American for the longest time. And I think that was, and I think that's where he probably honed his skills on recreational math and bringing math to everyone. And one of the other things that I found, which was really funny, he's, I think, one of the only known wizards that I know. He's actually been crowned a wizard of the unseen university. So welcome, Professor Ian. Welcome, and thank you for taking the time to be on our show. Thank you so much.
It's a pleasure. Thank you for inviting me.
So I think we'll probably get started by just asking you that when did you discover that you were good at math, and when did you kind of then take that leap to start making it fun for everyone else? When did that really happen?
I discovered I was good at it at primary school when I was about 9 or 10 years old. But I didn't really decide to make mathematics a career or even go to take mathematics as a degree at university until I was about 16 or 17. And at that point, I knew I either wanted to do mathematics or physics. And we had a very, very good mathematics teacher. His name was Gordon Radford. And he enjoyed having boys in the class. It was a boys' school. He enjoyed having boys in the class who actually were good at mathematics, because most of them weren't. And he spent a lot of his free periods at the school teaching us mathematics outside the curriculum, outside all the day-to-day stuff that everybody gets taught. And of course, that opened my eyes to the realization that there's far more mathematics out there than you ever see at school or in daily life. It's a huge subject. And that got me intrigued. And then I was offered a place at Cambridge University at Churchill College, which was a new college at that time. It was looking for grammar school children, which was me. So I went to Cambridge and enjoyed every minute of it. Then I did a PhD at Warwick University. Then they gave me a job at Warwick University, and I've been in the business ever since.
In India, we love math. I'm sure you're aware of the fact that everyone talks about math in India, but math is more about marks and mugging and making sure that you hit the 100 on 100 so that you get admissions into engineering college. And it's therefore always about pressure and not about passion. If someone like you had to design a math classroom for children to fall in love with math, because I definitely didn't fall in love with math in school, I just wanted to know, what would you want it to look like? What would you want it to be?
Young children are absolutely fascinated by numbers, by shapes, by colors, by arranging things, making patterns. I think that gets lost. It gets lost under the pressure of getting the answers right, passing the exams, getting a good grade on the latest assessment or whatever. I would like to see this playful side of mathematics develop better. So I think a little more time should be spent allowing the students to explore things for themselves, to play around, to do the kind of things that when I was doing the Scientific American column, making mathematics fun. Mathematics is fun. You don't have to make it fun. You just have to stop destroying the fun. So it would be nice if maybe 20% of the time was spent on that kind of thing. So mathematical play.
Oh.
That's something I never thought about. I never thought that you could make mathematics play. So that's a fun way to look at it.
So it's so interesting that you mentioned this. So of course, all our math and things comes out of movies and stuff. So there was this show I saw where this professor was teaching, and he was talking about pi. And so naturally, one of the kids raised their hands and said that, this sounds great, but where, what does it do for me? I have no relation to this number. And so he said something very interesting. And so he said that obviously pi is a non-recurring number. So he said that embedded within this number sequence is your life's history. It's your bank PIN number. It's your social security number. It's your girlfriend's birth date. It's everything that you ever know is hidden within this string. And then he said that if you now convert the numbers into alphabets, then it is the story of your life. It's the names of every person you know, everyone you've met, every place you've been to. And I And I felt that, that kind of completely changed your whole perspective on, about 22 by 7. And, that's all you ever think about. So, I mean, are there any other fascinating, and I'm sure there are like that, about numbers and theories and how they could be kind of explained to normal people?
Well, there's the very practical side, which all of the school teachers will tell the children, but they don't really understand. Many years ago, we were having our bathroom redone, and the man who was doing the tiles said to me, I've got to do a circular floor with tiles, and I don't know exactly how many tiles I will need. Now, I remember at school there was some formula they told us about circles and something called pi, and I think that probably would help. So I said, pi r squared, area of a circle. You can calculate the area, divide that by the area of the tile. That gives you the number of tiles. You better have a few spare ones because you'll lose bits at the corners. And he was astonished that this piece of schoolwork was actually useful for his profession. So that's the practical end. But pi is interesting because it turns up all over mathematics, lots of different ways. It turns up in probability theory, which has nothing to do with circles at all. It turns up in anything to do with circles. It turns up, I do a lot of work or at least until recently when I changed my main research area, I did a lot of work on pattern formation in physical systems, chemical systems, this kind of thing. You can get beautiful patterns appearing in, say, a circular dish full of liquid if you vibrate the liquid. These patterns are governed by trigonometric functions, which is another thing we do at school. And trigonometric functions are all about circles, and circles are all about pi. And you just cannot get away from pi. So it's fascinating in its own right. There are people who try to break records for the number of digits of pi that they calculate.
Right.
This is completely pointless practically. You do not need 1 billion digits of pi for any practical reason. But it's possible to do this is amazing. And some extraordinary formulas and ideas have come out of this quest for lots of digits of pi. There are formulas for pi which they're a series. You add a number, then a second number, then a third number. The numbers get smaller and smaller. You add them all together, stop at some point, and you get billions of digits of pi very, very quickly.
Okay.
So these formulas are quite amazing. And most numbers in mathematics don't have formulas like that. So pi kind of stands out in the mathematical landscape as different from everything else. It's very unusual. There are a few other numbers like that, but pi, it's the first one we meet. It's one that has a geometric meaning, and we still don't understand an awful lot about it.
Maybe they can
So there's a challenge.
Maybe they can make a movie called The Life of Pi, but which is based on the number and not on the character, I think. Might be interesting.
That's a great idea.
Ian, also wanted to check with you. So, math, I believe, is the backbone of technology. And that's what I keep hearing. Everyone keeps saying math is the backbone of technology. And I just can you give us one or two real world tech breakthroughs that couldn't possibly exist if we didn't have math? Something that will make even the math folks say, like, really? Even that is math? That kind of stuff.
Okay. Well, the internet would not exist without maths. Computers would not exist without maths. They would not exist without brilliant engineers, very clever people who are not mathematicians, but the mathematics is embodied in the structure of the technology. So deep inside your computer is a logic chip which does numerical calculations, and it just does logic. The whole of computers is based on binary logic: yes, no, true, false, 1, 0, and everything else comes from that. A less well-known one, satellite navigation. You're driving in your car, you now have a screen which shows a map, which shows exactly where you are. It shows where you're going. It tells you how long it's going to take to get to your destination. There are, probably 8 or 9 different areas of mathematics involved in making satellite navigation work. One of them is just how do you find the shortest journey between point A and point B on a map? And this is an area of mathematics called graph theory. Another one is the way satellite navigation works is the satellite sends signals to your car, and from the signals you can work out the time it takes for the signal to reach your car. That gives the distance from the car to the satellite at that instant. If you have 5 or 6 satellites, it's usually 30 or so. Those distances put together let you calculate exactly where you are on the surface of the Earth. So that's trigonometry. That's something we do at school. It's 3-dimensional geometry, but it's a very sophisticated and subtle and clever use of it. And of course, making it work at high speed when you're driving along the road involves a lot of other things that are nothing to do with the basic maths. None of those calculations would work without Einstein's relativity, which is a mathematical theory. In fact, he has 2 theories, special relativity and general relativity. Special relativity is about what happens when objects move very, very fast. Well, light signals move very, very fast. Satellites move quite fast. General relativity is about effects of gravity. Well, a satellite goes round and round the world because of gravity. Einstein's theories are slightly different from the classical theories of Isaac Newton, which, until 50 or 100 years ago were the way to do all these things. Satellite navigation does not work unless the mathematics takes care of the difference between Newton's theories and Einstein's theories. You need both special relativity and general relativity to make the thing work. Now, special relativity is largely about partial differential equations, it's called. General relativity is what we call Riemannian geometry. It's the geometry of curved surfaces, curved spaces. So about 8 or 9 different major areas of modern mathematics, most of which nobody's ever heard of, are embodied in your satellite navigation system. All you have to do is push a few buttons, and the mathematics embodied in the electronics and up there in the satellite and everywhere else does all the work for you. It's a great shame if people realize the maths was there, they have a very different view of the subject. For many years, I said we should have a little red sticker which says maths inside, and we should stick it on anything that uses maths, and the world would be covered in little red stickers.
That's such a brilliant idea, because I think kids will then realize that there's math in everything that they do. But having said that, I do want to understand AI, which also has a lot of math in it, is slowly taking over everything. Do you think that, I'm just trying to figure whether the world of AI is going to replace the world of mathematics, or is it going to give us even more challenges, or is it going to be that now instead of professors, we'll have AI teaching us mathematics? What's going to happen with AI, which takes so much of mathematics to get developed?
I think the problem here is that it's very hard to see in advance. We can see the dangers, we can see the advantages, we can see the potential. Yesterday evening, I was sent by a mathematical colleague of mine. We've been having a discussion about an esoteric area of mathematics and wondered what was known about a particular topic. So she asked an AI system, and it printed out about 5 pages worth of actually very interesting and correct description of the whole area, which if we'd been searching online for all the different research papers in which this stuff appeared, would have taken days. So it's a very powerful technique for some purposes. My biggest worry is not so much about AI putting mathematicians out of work, although it might. I don't think it will, but it might. It's about it putting lots and lots and lots of other people out of work. And I do feel that governments worldwide have missed a trick. They should have regulated it from day one. I don't think it should ever have been released to the public without proper regulation, because there are so many ways to abuse AI. There's a growing realization that an awful lot of the work you can get AI apps for almost anything now. most of them have not been tested properly. Most of them have not been benchmarked properly. Most of them have not even been analysed statistically to see whether they work properly or not. So there's a danger people are being sold things on false promises. But having said that, there's an enormous range of very important applications in medicine, in mathematics itself, in the sciences, where AI is already adding things that are important for everybody. So it's getting this balance between the dangers and the damage and the positive applications. I don't have the wisdom to say how that should be done. I do feel at the moment that the governments, as always with new technology, they are behind. They wake up about 10 years too late and start trying to regulate things that have already escaped.
That's so true. That's because the governments don't even know the technology that is getting developed, and I think that's the biggest challenge. People developing the policies don't really have a clue as to what's coming.
One way to say that, I think this is a slightly cheeky thing, but we need more mathematicians in politics.
So it's so strange that you say that.
Mathematically educated politicians in politics.
So in fact, I just read something very recently as to what is the fundamental difference between American politicians and Chinese politicians. So they said the fundamental difference is that all Chinese politicians are engineers while all American politicians are lawyers. That's the reason why China builds stuff and America just debates stuff. And that seems to be, I think throwing mathematicians into the mix would make a big difference.
I'd like to think so. Yes. There are always exceptions to these things, but as a very broad characterization, you can't help feeling that, yes, indeed, there's a certain truth in that statement.
No, so it's true. So all thanks to really the impending conversation with you, we both landed reading up a lot more about math, and we found there are just so many interesting stories, and I think stories makes the subject interesting. So I just came across this thing about this, I think he was French, this gentleman called Gallo, who actually, he was supposed to have a duel the next morning, and he knew he was going to die. So the last thing he did was he wrote down all the mathematical ideas he had the previous night, and lo and behold, two of them went on to become branches of mathematics. So, it's, well, of course, unfortunately, tragically, he died the next day. But I mean, that's the level of craziness and passion and the interest that math raises. And the other thing, sorry. No, go ahead.
No, Galois a very interesting figure. Yes. I mean, it was just before his 21st birthday. He had a duel with his friend over a young woman that I think they were both interested in. And Galois lost, yes. But instead of having a good night's sleep, or at least trying to, he wrote a letter to another friend summarizing all of his mathematical discoveries. It then took something like 40 years before one mathematician, looking through the documents he left, looking at this letter, said, this chap actually had a really good idea here. This is important. And it founded a new branch of mathematics. Yeah. But you're right about stories as well. Mathematics done by mathematicians, especially pure mathematicians, is about proving things. I always talk about proof. True. Yes, it's not enough to state some important theorem. You've got to have a proof. The reason we've got to have a proof is because otherwise you don't know whether it's true. We can't do an experiment like a physicist or build one like an engineer and see if it works. So we need very, very strict proof. There are lots of descriptions of what proofs are, but my view is a proof is a story. It's a story that says, okay, let's assume at the beginning we have a right-angled triangle. At the end of the story, we have Pythagoras' theorem that the squares on the two sides add up to the square on the longest side. But in between is the rest of the story, which links the beginning to the end, and that's the proof. And proofs should be presented as stories so that people can understand them. People like stories.
Oh, speaking Speaking about Pythagoras, I have to ask you this question. Uh, I'm sure millions like me want to ask you this question. Why did I study the Pythagoras theorem? I've never measured a hypotenuse in my life, ever. So I just want to understand, why
Okay.
did I study it in school?
Okay, you studied it so that you were one of the people who might later on become an engineer who would build something like satellite navigation system, which among other things uses Pythagoras' theorem to work out how far away the satellite is. Everything in surveying, map making, navigation is based, it goes back to the geometry of Pythagoras' theorem and then what came later. So, I mean, real navigation, let's say an aeroplane flying around the globe, to a good approximation, the Earth is a sphere. It's not a plane as Pythagoras' theorem would work. Pythagoras' theorem isn't even true on the sphere, but something like it is. And if Greek geometry, if Pythagoras and his followers had not, or whoever actually discovered Pythagoras' theorem, it's probably earlier, but he gets the credit because he was the guy who ran the big school that had the idea that mathematics is the basis of everything. If Pythagoras and others had not investigated the simplest case, which is right-angled triangles in the plane, we wouldn't have had spherical geometry. We wouldn't be able to navigate around the globe. But any one individual doesn't really need it because somebody else has already done it for them. This is, in a sense, the tragedy of mathematics, but also the reason why we teach it to everybody so that it's not. It would be horrible if teachers said to children at the age of 6, "You're no good at maths, you don't need to do it. Go off and do something more interesting. Oh, and by the way, here is a list of all the professions that you will not be able to have when you grow up. You can't be an airline pilot, you can't be a doctor, you can't even be a lawyer. As my wife discovered, you can't actually be a nurse." So my wife in a former life was a nurse. When we got engaged, her mother asked her what we had in common, and she said, "It's not the maths." Maths was not her best subject. But later in life, she became an ophthalmic nurse. She worked on eyes, and she had to learn the mathematics of optics, a little bit of it, and she had to learn the mathematics of how genetic eye conditions are propagated from one generation to the next. And suddenly, a large amount of the school maths that she'd done became important for what she was really interested in. And that changes people's attitude completely. It doesn't change their attitude to the whole subject, but it changes their attitude to those bits of the subject that they actually need, that they use. My son is a computer programmer. He uses a lot of maths. He didn't actually like maths as much at school, but he was quite good at it. He was much more interested in computing and engineering. And what he really likes is building things with his hands. He built himself a gymnasium in his back garden.
Wow.
A big hut, roof, floors, everything. He's an engineer at heart. But he uses sophisticated maths, but he's only interested in the maths when it's useful to him. But all of it's useful somewhere. So and to stop people being excluded from whole areas of human activity, you get dragged through maths at school, whether you like it or not.
On that, let me ask you this question. Is there an equation out there which should have got more credit than it did in school?
Something that gets more credit than it has?
No,
Sorry,
something
can you
that
repeat the question?
I said, is there an equation out there that should have got more credit than it ever has
Should have
had in
got more
school?
credit.
Yes.
There are many, actually. Most of the ones don't get credit in school because we don't do them in school. I think my favorite here, which in school physics we do a little bit of it is called the wave equation. So this started back in the 1700s with a mathematician or two or three mathematicians they were actually in competition with each other. The mathematicians of those days were, it was all one-upmanship. It was, can you prove this before I do? Can you solve this equation first? They set each other challenges. But They were looking at how a violin string vibrates. They weren't even looking at a real violin or a real string. They were looking at a mathematical line fixed between 2 points, perfectly uniform, vibrating in a very, very small amplitude oscillation, just very tiny movements. And they wrote down an equation for the violin string. It's called the wave equation. It's a very pretty equation. The same equation turned up, 200 plus years later, round about that, no, maybe 200, in radio waves, in electromagnetic radiation, in light, in radio, and that equation was what told the physicists that radio waves existed. They had equations for electricity and magnetism. They messed around with them and out popped the wave equation. And they looked at that and said, oh, I recognize the equation. That's waves. There must be electromagnetic waves, but we've never detected them. We've never created them. What can we do to test this mathematical prediction, basically? Well, the equation has in it one number, which is the speed at which the wave moves. And they could calculate that number from the electromagnetic information, and it turned out to be almost exactly equal to the speed of light. So here's a question for you. What moves at the speed of light? Light. Yes, it's like, obviously. Right. Who's buried in Lincoln's tomb? It's that kind of question. So literally the little light bulb goes off and the physicist, light must be electromagnetic radiation. This is completely unprecedented idea. They couldn't test that with light, but they could test it with longer wavelength waves, which gave us radio, radar, television, and nowadays the internet, satellite navigation again. All of modern communications happened because a mathematician had a completely ridiculous, oversimplified model of a violin string.
Wow.
That's how it works.
So I would imagine that one of the things that drove you to write the column on recreational mathematics is just making it easier for everyday people. And I think make everyday people feel smarter, and it's literally like party tricks, right? So I think I would imagine that something like that birthday paradox, that, how many random people do you need to find a common birthday? And apparently that number is 23, and that's mathematically true. So are there things like that which if you could probably share off the top of your mind that would kind of, make people feel, wow, that's a question I can pop, and, it'll be so cool to know the answer, and maybe that'll get them to love math.
Yeah, that one's very nice. I tested this in a program done for the BBC with 500 children in the audience. And when they came in, they wrote their birthday on a card. And we didn't just say that you need 23 people for it to be more than 50% likely that two of them will have the same birthday. We predicted the number of cases where, essentially we predicted things like there will be 12 of you who, there will be a birthday that is shared by 12 people. There will be various combinations of birthdays where we did the statistics. Mm-hmm. And we predicted this at the beginning before they filled in these forms. And then somebody did the sums during the program. And then we put up the answers at the end. And we had successfully predicted the entire distribution of birthdays across the audience and the coincidences between those. So it really works. There's a friend of mine who says, so when you're looking at a football match and there are 22 players on the field plus a referee, forget the others, it's 50-50 that two of them share a birthday.
Wow.
So when you watch a football match, and you can check this, you can look them up and find their birth dates and see whether it works. A very famous one is a thing called the Monty paradox. This was an American game show. So the contestant is shown three doors. Mm-hmm. One of them has sports car behind it. The other two have a goat behind. And the idea is that it's completely random. The sports car is as likely to be behind any door as behind any other door. So then the host says, okay, now choose your door. So the player chooses a door. And he then says, okay, let's forget that door for a minute. Let's look at the other two doors. I know where the car is. At least one of the other two doors has a goat behind it because there are two goats. So I'm going to open a door that shows you a goat. So he does. And then he says, now that you've seen that, would you like to change your mind? Now, there's a lot of psychology and there's a whole lot of other things that need to be thought about here. He might deliberately only do this when you've chosen the car. I'm assuming people want a car, not a goat. I mean, there's some cultures, the goat would be what everyone wants. Okay. If you do the sums, and it's very hard to wrap your head around, if this is done honestly and there's no cheating, when he opens the door to show you a goat, it turns out that changing your mind doubles your chance of winning. Because before he did that, the chance you'd chosen the car was 1 in 3.
1 in 3.
So there's 3 doors. After he's fiddled around with the other doors, it's still 1 in 3. Because that's the door you chose. That's where the car was or was not from the beginning. Which means the only remaining door will now work 2 times out of 3. So it's a better choice.
So it's very...
So I talked about this on radio, and I got an email almost immediately from, about 2 hours later, from somebody who said, me and my mates were in the pub and we were listening to your radio broadcast, and my mate said, that's ridiculous, that's not possible. So we simulated it on a spreadsheet, and lo and behold, you're right. And I'm thinking, this is an interesting bunch of people. They're in the pub. They've got their laptop with them. They do spreadsheet simulation. These were clearly city bankers in London who were out for the evening, but they were listening to the radio. It was extraordinary. But it would also so they did 1 million simulations, and 666,000 times swapping was the better choice.
Wow.
So it's so strange again that you mentioned this. So maybe you are aware, but there was this movie by Kevin Spacey called 21. And this is the very question that he poses, because he's trying to pick card counters. So he wants to get people who are very good at math. So he uses he puts that to the students, and one of the students gets it right. And of course, the answer there he says is that it's about variable change and whatever. But it's the same thing. I mean, he uses this question to filter, to figure out who is the smartest kids in the pack who can become great card counters, because he wants to go and cheat the slot machine, the machines at Vegas.
Yes. I love it. Yeah, that's right. It's about conditional probability. It's about the probability of something happening when you have extra information that something else has happened. And human intuition about probability is not very good. Human intuition about conditional probability is appallingly bad. My own intuition about conditional probability is bad. And I know the formulas. I know how to calculate it. You do it and you look at it and you think, is that right? Did I do the sums correctly? It just says, yes. Again, we live in the information age. This is all about information. When the host opened a door, he gave you extra information about what was happening. If you've got extra information, you should be able to improve your chances of winning. And that's the principle that underlies card counting as well. Yeah.
On that note, I have to ask you, just for laughs, have you ever got, or has there been a time when math has failed you? Like you misjudged a probability, or you didn't park your car correctly because you got it wrong? Where has maths gone wrong for you? Just for laughs.
Oh, Lord. Let me think. I think it has saved me in the sense that I am For example, I don't bet on the lottery. There is a national lottery. You can win millions and millions and millions on the lottery if you happen to be the one person who wins. So I do the sums and I realize that on average, I'm going to throw away about 10 times as much money as I could possibly stand to win. So I decide not to waste my money. Yes? Okay. And it's a rational position. It's in the long run, if I say this to 1 million people, nearly all of them, it will be good advice. But one of the secretaries in our mathematics department bet on the lottery and won £500,000.
Wow.
If I had argued this to her, I would have been giving her very bad advice. So what I actually say to people when they are, you're a mathematician, what do you think? I say, if you can afford to lose and if it's fun betting, then there's no harm in it. Why not? But you should be aware that the people running the lottery are the ones who have the guaranteed profit. Almost everybody else will lose. There will be a small number of winners. The losers have paid for the winners and the company is still taking its profit. Do you want to be involved in that? And of course, a lot of people answer, yes. And I can understand why, because if it does happen to be you who wins, your entire life is changed. And probably in a positive way. I mean, I wouldn't turn it down. Even if, there's an argument that it's such a huge sum of money that not only is your life changed, but basically you may have trouble coping with it. And this is human psychology and it's true, but even so, it's not a good reason for turning the winnings down. I think you just have to be careful what you do afterwards.
So this
not get carried away.
So the story of probability and psychology is very interesting. And again, I'm sorry, all my examples tend to come from movies because I watched them. So I very distinctly remember the situation in a movie where there was this kind of a buffoon and there were these smart guys and they were trying to demonstrate to each other how that buffoon is a buffoon. So they say that, we offer him 25p and we offer him 1 rupee. And guess what he takes? He always takes the 25p. And they kept on doing this. You said, see, I'll prove it to you again. I'll prove it to you again. And then towards the end of the movie, the story flips towards the side of the buffoon. And they said that, did you know that 25p was better or the 1 rupee? He said that if I had taken the 1 rupee, would they have offered it to me 20, 30 times? So I made more money. So he obviously had the smarter thing going there. So,
that is absolutely brilliant.
So I mean, that is, wow, that's probability and psychology working in a very practical manner.
There is a serious message in there which mathematicians need to be taught, which is it's how you model the real world with your mathematics that counts. If you set up the wrong model, you will get the wrong answer. And so the two sides there had different models in their minds.
Absolutely. So that's something really
it's clear who had the best one.
Ian, you've written about 17 equations that have changed the world. And I tried to go through all 17, and I promise you I ended at 5. I knew only 5, as in I'd learned or read about 5 of them. But what I really want to understand is if you had to pick 2 of those equations, and I did, read quite a few of them, but if you had to pick 2 that you feel have transformed life the way we see it now, without which, we couldn't possibly exist or exist the way we do. And you've spoken about, math in all the other spaces, but which are those 2 critical equations that you think that if we didn't have them, we'd remove everything and the comforts that we have would disappear? So I'm doing the Thanos version of dealing with the world. So 2 mathematical equations that would wipe out the world as we know it.
I love all 17 of them. It could have been 30. My big problem was cutting the numbers down. Okay, I've already mentioned the wave equation, so let's exclude that one because I've already talked about it. So I've got to come up with 2 others.
Yes.
Schrödinger's equation in physics, which underpins the whole of quantum mechanics, which is how all of our computers now work. That's one. And I think I'm going to go right back to Pythagoras' theorem and say,
Okay.
actually, that's the great granddaddy, great grandmother of all mathematical equations. It's almost the first one at school that we ever come across that has any real significance. It gave the world navigation. It let Columbus, well, Columbus used rather bad geometry of the globe to persuade Queen Isabella to fund his voyage where he discovered America. He thought he was discovering India, a different route. But it was part of the culture at that time, and it was part of how human beings understood what the planet looked like and how to get around on it. It opened up all of that. So I think, as I say, it's called Pythagoras' theorem. It's certainly true that the Pythagorean school of mathematicians that he inaugurated knew about it. It's not clear they proved it,
Okay.
but they
Okay.
knew it was true, and they probably had pictures that would demonstrate it. But I think they deserve an awful lot of credit for just opening up the whole world of mathematical equations, on which, as I've been saying, and you've been agreeing, our lives depend in a way that we don't normally notice because the maths is not sitting there on the surface.
Right.
You go along a street, you see signs saying greengrocer, doctor, optician, whatever. You never see a sign saying mathematician on a shop in the street. You can't go in and buy mathematics. But everything you buy has mathematics inside it.
I can see Samiran putting on a t-shirt which says math, something to do with mathematics. He just loves these crazy t-shirts, and I can just see that the next one is going to be on mathematics.
So, obviously, unfortunately, we are also moving to an era where everything's at the click of a button. And there was a time when we used to remember everyone's telephone number, and now we don't because everything's fed into a phone book. So our memory for numbers as well as our need to know pure math is going away because we're trying to kind of get everything off the internet or off some tool. What would you recommend, or what do you think works to get children or the next generation interested or fascinated with maths? I mean, and not for all the practical reasons, I mean, how do you actually make it fun? What are like the, 3 tricks, or maybe is there anything that will get the general population interested? And we're not talking obviously about the proven geniuses who are good and they know it, but just the general population.
There was a conference at Warwick University a few weeks ago, run by an organization called Talking Maths in Public. And you should look this up. It's not just about talking maths in public. It's exactly about what you've just asked. It's about, if we want to go out to the public and interest them in maths in some fun way, it's got to be pleasant for them. It's got to grab their attention. They've got to think, oh, that's cool. Yeah, I like that. There were about 150 people at this conference, and they were the practitioners. They were the people actually doing this. So nowadays, there's a lot more going on than meets the eye. The one I really liked was somebody gave a very short talk. It wasn't a talk, actually. He just demonstrated. He goes into schools. He goes into the sort of 5 to 12 age group schools. So very young children. And he takes a big bag with him. And in his bag are mathematical magic tricks. And he doesn't just do the tricks. He explains to them exactly why the tricks work. He shows them the secret, but he does the trick first. And the one he particularly showed us, which went down fantastically well with 150 people who knew mathematics backwards, was he reached into his bag and he started pulling out a cylinder. And he kept pulling out this cylinder, and it got longer and longer and longer until it was twice as tall as he was. And then he said, okay, so I show this to the kid, and you see them Mouth open, eyes wide. How did it get in the bag? Right. And then he folds it up, and the cylinder is slit all the way down. And if you take the bottom and you twist it, you can fold it up the other way. And you end up with something about the size of a toilet roll, and that goes in the bag. But when you pull it out, it automatically springs into the other shape. So he had a whole battery of things like this. But you can, as I say, he then explained how it worked. He explained, so suddenly they're learning about cylinders. They're learning that things can form different shapes. So that was one level of that. So there's a lot of information out there already available through organizations of that kind, and people are out there every day doing it. On a slightly more educational level, a higher level, in the UK we run things, other countries do similar things. They're called mathematics masterclasses.
Right.
They started as classes for the very, very talented children, but they've turned into classes for anybody, but they've kept the old name. There are an enormous number of these running around the country, and the way they work is about 30 children spend 10 mornings, usually Saturday morning, 3 hours, 2.5 hours, being shown mathematics that is not part of the school syllabus. I taught this many years ago. We did things like knot theory with them. We did a little bit of graph theory. We did a thing called Pick's theorem, which is lovely. You take a rectangular array of dots, you join dots to make a shape, and then you calculate the area of that shape by counting the dots. Not by actually working out the area. It's a triangle plus a square plus whatever. And there's a formula for that, which ought to have been in my book, but couldn't be. There wasn't room. 17 was the most we could cram in. So at a slightly higher level, there are activities going on, and there is material on the internet about this. In fact, a former PhD student of mine who's a colleague at the university and I are putting together a book based on notes from the masterclasses that were done at Warwick. So at some point next year, there should be a book of this material. So this is probably best for the sort of 13-year-olds and upwards. And roughly speaking, the older they get, the less good at mathematics they have to be,
Right.
because they've absorbed a more sophisticated view of what mathematics is, so that they can tackle slightly more challenging topics.
Ian, I think we can continue on this conversation and keep you here for hours. But for our listeners, I thought we'd end on a fun thing. We're going to ask you 5 very quick questions, and you can give us really short answers for that. And with that, we could possibly end this episode. And it's all about, think of it as math in a minute. Okay. So
Okay.
just quick 5 questions that we're going to push out at you. And the first one is, what is the most beautiful equation ever?
What everyone says is the most beautiful equation is Euler's equation, e to the I pi equals -1, because it links all of the important mathematical constants. E is a rather funny number like pi, but it has a different significance. I won't explain it. Pi we know, 0, 1 we know. So it links them all together, and it's a total surprise that there's any connection.
Okay. A math idea that you think everyone must know.
The Banach-Tarski paradox.
Okay.
You can take a solid sphere and cut it into a small number of pieces. I think 7 will do the job. And you can reassemble those pieces without changing size or shape to make 2 spheres exactly the same size as the original one.
Wow.
Wow.
And everyone says, that's impossible, that's completely crazy because the volume has doubled. And the answer is the pieces they're not like you cut off with a knife or something like that. They are extraordinarily complicated mathematical objects, which are so complicated they don't have a volume. They don't have a well-defined volume. So you can't argue about the volumes anymore. It's completely bizarre, but it's true.
That leaves, I mean, I don't even know how to react to that.
Everyone's free to say that's completely ridiculous. I don't. You need you need to be somewhere at master's level in a mathematics degree course to actually understand precisely what's involved in it. Yeah.
Which I'm not getting anywhere in this lifetime.
No.
One math myth that you would like to destroy.
One math myth: it's not useful.
Nicely said.
Nice. You spoke about proof and more proof that mathematicians need. Proof or intuition? What's more fun?
Intuition is more fun. Intuition is what actually tells you what the answer is or what you should be trying to prove. And often in mathematical research, the biggest problem is not coming up with the proof, it's working out what you should be proving. So intuition will give you that. Then you try to you go for a proof to check your intuition is correct. And surprisingly often it's not. And there are occasions when everyone's got the intuition and 300 years have passed and nobody's got a proof yet. So there are these famous big unsolved, the thing called the Riemann hypothesis, doesn't matter what it is. It's been around for a couple of 100 years and nobody knows. We don't know whether it's true. All of the evidence is that it should be true, but there's no proof. There's no disproof. We don't know.
And my last one. If math, and this is because Samiran is a big movie buff, if math were a movie genre, what would it be?
Oh, Lord. Okay. It would have to tell very good stories about mathematics. Yes. If you haven't got a story, I once wrote a paper, you can find it, retelling the nursery story of the three little pigs and the big bad wolf. Yes, the little pig. There are three little pigs. One builds a house of straw, one builds a house of sticks, one builds a house of bricks, and the wolf blows down the house of straw and the house of sticks, but the house of bricks stays up. There is a children's book which is illustrated, which tells this story. I got permission from the publishers to use all of their pictures, but rewrite the story in mathematical terms and rewrite it in. But I did it deliberately in very bad mathematical style. That is, it starts with 5 pages of definitions before you start to get to the actual story at all. And then the whole story is collapsed into the last couple of pages. So it was meant to be a way of saying that a lot of our mathematical writings are actually very bad in terms of storytelling and therefore difficult to read. If you put all your definitions and stuff up front, even I'm sitting there looking at it thinking, why are we doing this? What are we going to do with these things? You know, you define this structure, this object has some fancy name, but I don't know. I have no idea what it really is yet. So I think mathematicians should tell their stories better, and maybe a movie could do that.
Nice.
Yep.
I love it. I'm going to find that book for sure. Ian, it was an absolute pleasure having you here today. I will start looking at math differently, I promise you, just because it's such an eye-opener to figure that, oh my God, everything that you do really has mathematics involved in it. Thank you so much for being here and having this wonderful, wonderful conversation with us.
Oh, thank you. It was great fun at my end. You could tell that, I'm sure.